right, so in the previous video, we did the simplex method for finding the optimal solution and the optimal objective function value for a maximization problem. Now we're going to do the same thing using the simplex method for a minimization function, and you'll find that it's very, very similar, except for a lot of the rules and conventions are reversed. Right, because we're doing the opposite, we're minimizing. So first, what we will do is, you'll notice that unlike the maximization function, typically speaking, the left side of the constraint inequalities are going to be smaller than or equal to the right side of the inequalities. Once again, if you're faced with a situation where one of the constraints is smaller than or equal, there are ways to convert that into bigger than or equal, which can be discussed separately. But for now, let's tackle this. So our first step, as usual, is to get the augmented form. If you watched our previous video on maximization and the simplex method, you will be very familiar with this. And so in the augmented form, we want to turn these inequalities into equalities. So let's go ahead and write that. We're going to have 3 because we have 3 constraints. So we're going to have 2x1 plus 3x2 equals 242. Now, we know that the 2x1 plus 3x2 is bigger or equal to 42. So if it's bigger and we want it to be equal to 42, we would have to subtract something, which is why, unlike in the maximization simplex method, we will subtract a slack variable, a basic variable, a slack, S1. In the maximization, we added one because it was smaller. We're trying to make it equal. It's one of the things that changes is the reverse, right? So we're going to have 3x1 plus 4x2, this is for the second constraint now, minus slack variable 2 equals 60. And finally, x1 plus x2 minus s3 equals 18. This goes without saying, but xi and si are bigger than or equal to 0 for all I equals 1, 2, and 3. So now let's write out our first dictionary. So our dictionary is going to be what we have in the augmented form, but solved for S1, S2, and S3, our non-basic slack variables. Our basic slack variables. We have S1 is going to equal 2x1 plus 3x2 minus 42. It's 42. Our S2 is going to equal 3x1 plus 4x2 minus 60. Then we're going to have S3 is going to equal x1 plus x2 minus 18. The non-negativity constraints follow through. And that is the end of the dictionary. So now that we have our dictionary, we can start our first iteration by picking an entering variable and solving for it and figuring out what its minimum value is going to be, and etc. So remember, the simplex method basically takes out all of the variables, equates them to 0, and starts re-entering them back into the model and checking what values they can take on without violating constraints. Since it's a minimization problem, though, unlike the maximization problem, we're now, pardon me, we're now going to be looking for what is the minimum value that these variables, x1, x2, can take, right? So we will have to, first of all, pick our entering variable, right? And once again, because it's a minimization problem, we will pick the first entering variable to be the one with the smallest coefficient in the objective function. In this case, it's x1 as its coefficient is 5, which is less than that of x2, which is 7. So we can have our iteration 1 here. So we'll start our iteration 1 there and then go line by line. We have entering variable is going to equal x1. Now, what we have to do is to ultimately solve solve our dictionary for our slack variables to get an idea of what it's going to look like, and then we're going to set up our if-then comparison. So if we have our entering variable equaling x1 and all other non-basic variables still equal 0, right? We have that at the moment that our x2 hasn't entered yet. It's just still equal to 0. We will have the following. This is the following of iteration, still in iteration 1 over here now. So we will have that S1 is going to equal 2x1 plus 3x2. This goes to 0, right? Because 3 times 0 equals 0 minus 42. Then we're going to have S2 equals 3x1 plus 4x2 goes to 0 minus 60. Then we're going to have that S3, pardon me, S3 is going to equal x1 plus x2, which again goes to 0, minus 18. Feel free to fast forward to these steps if you're very familiar with them. So now we set up our if then. So if and then. So here, since it is the opposite of a maximization function, we're looking for what value of our entering variable x1 is s1 going to be less than 0 and therefore violating this constraint. We're looking for the minimum value of, and we're going to, at the end, we're going to be looking for the minimum value that x1 has to take. So in the first one, we're going to have x1 must be smaller than some value such that S1 is smaller than 0, right? So if we solve in this section for x1, it would be 2 times some value of x1 minus 42. So what does x1 have to be for it to equal 42 or more than 42, right? Because you've or less than 42. So for example, if it equals 21, S1 is gonna equal exactly 0. But if it equals anything less than 21, for example 20, then S1 is gonna be lower than 0, and that cannot happen because of our non-negativity constraint. So the value below which we cannot go on x1 is 21, right? This is the minimum value in this constraint. The minimum value for x1 is 21. Then we're gonna go with the next constraint. For what value of x1 is S2 smaller than 0? So what do we have here? 60. So 3 times what is going to equal 60? And that'll be 20. If it's, let's say, 10, it'll be negative 30, which, because it'll equal 30 minus 60, S2 cannot equal a negative. So, pardon me, this is 20. So that is the minimum value of x1 for with regards to S2, and for x1 and S3. Here there's no coefficients, so it's 18. So now ask yourself the question, what is the minimum value that x1 can take without violating any of these constraints, right? Including this one. This is the key. If x1 takes 20, we know that over here it's going to equal 2 times 20, 40, minus 42. It's going to equal if equals 21, this constraint is satisfied. Pardon me. This constraint is satisfied. S1 is going to equal 0, which is okay. But if it equals 20 or 18, based on this constraint, this will be violated. In fact, if it equals 20, if it equals, this constraint will be violated. If it equals 18, both of these constraints will be violated for this, right? So therefore, the minimum value that x1 can take is 21, right? It's this one. So now we take the constraint that corresponds to that if-then comparison, and we solve for the entering variable x1. So that's going to give us, that is going to give us that x1 equals S1 over 2 minus 3x2 over 2 plus, that's correct, plus 42 divided by 2 to isolate x1, so that's going to give us a 21. So this is now our expression for x1. So if you remember from the other video, next we will start by plugging this into the objective function, which we have up here. And this time, unlike in maximization, we're going to be looking for all of the coefficients of any variables in the objective function to be strictly positive. So in the maximization, they had to be negative for it to be optimal. In minimization, it's the opposite. It has to be, they have to all be strictly positive. So here we go. Minimization of z equals 5 times this expression for x1. So 5 times s1 over 2 minus 3x2 over 2 plus 21 plus 7x2. 7x2. If we multiply the 5 through and add the whatever the values of the x2 are going to be, it's going to give us that z equals 5 over 2s1 minus 1 over 2x2 plus 105. So I think we can agree that because of this negative coefficient on x2, x1 equaling 21 is not an optimal solution. And thus we need to do another iteration. So for the next iteration, we're going to have to set up our constraints. So we will have to plug the value of x1 into the other two constraints. I will not do the expanded version. I will directly plug it in and give you the multiplied through version and everything for those two constraints. And we do not need to, well, I guess I'll write the entire thing actually. So subject to x1 equals s1 over 2. Remember that this is the first constraint. That's already the subject. x1 is already the subject of this iteration. So we can go ahead and just copy it down. Minus 3x2 over 2 plus 21. This is our first constraint. Our other two constraints are going to be, so just a quick reminder, since this is not optimal, this now becomes our second iteration. So as of right here, iteration 2. Okay. So continuing with our constraints, which will become our new dictionary, the one that we're going to use for a second iteration, we're going to have 3 over 2 s1 minus 1 over 2x2 plus 3. And our last constraint, the third constraint, is going to be s3 equals s1 divided by 2 minus 1 over 2x2 plus 3. The non-negativity constraints also follow through. I don't have that much space on this board, so I will not write them, but write them on your exam because professors will take points off for that. All right, so it goes without saying that in this iteration, x2 is going to be our entering variable, not just because it has the smallest coefficient in our new objective function, but also because it's the only non-basic variable we have left, right? We already did x1 in the previous iteration, so we could just note that over here, entering variable equals x2. So now we know from here, we're going to be using these two constraints to figure out what the minimum values for x2 are going to be, so that this equality stands. So since this is this equals 3, and this is a multiplier of half of x2, our minimum value for x2 is going to have to be 6. So we're just going to have, instead of the if-then tables, minimum value for x2. All right, so for this one, it's going to be 6. x2 equals 6. And for this one, x2 has to equal 6. So it's quite easy here to figure out that for this iteration, our x2, what we're going to be testing is that our x2 equals 6. So that is the minimum value that x2 can take without us violating any constraints. So we need to rewrite the second constraint, this one, also seen over here, and solve for x2. Ultimately, also our leading variable is going to be, we could just pick any one of the two, but our leaving variable here, I will pick it because they're equivalent. Our leaving variable here is going to be variable equals, let's go with S2. Doesn't really matter, but S2 as their equivalent. So moving forward, we're going to have our expression for, I'll use a different color. We're going to have our expression as what we did here, but for x2. So x2 is going to equal 6 plus 3s1 minus 2s2. Right. We then go ahead and plug this into our objective function that we have over here, and then see and multiply everything through to see our coefficients. So what we will wind up with is minimizing z equals 5 over 2 times s1 minus 1/2 of x2, and that's going to be this. So it's 6 plus 3s1 minus 2s2 plus 105, a constant. If we multiply this 1/2 through, for x2, we will get z equals 102 plus s1 plus s2. So we've reached optimality. As we can see, all of the variable coefficients are positive. And so now we know that x2 indeed equals 6. So the last thing left to do is to plug in x2 for the x1 and solve for x1, knowing that our leaving variable s2 is already gone. Our s1 equals 0 from the previous iteration. So we're going to use this constraint and solve for x1 by plugging in the value of 6 for x2. So what we will have is x1 is going to equal S1 over 2 that we know is 0. We're going to have minus 3 times the x2, which is 6, divided by 2, plus 21, and we'll get a value of 12 for x1. This is our value for x1. So that means that our optimal solution, meaning the values of x1 and x2, is going to be, I'll write it over here. So optimal solution is going to be 12 and 6. Finally, if we plug in these values 12 and 6 into our objective function, we will get that z, I will not write out the whole thing, it's 5 times 12 plus 7 times 6, which will yield 102. If you would like to check the validity of the solution and make sure that all of the constraints are not violated, you will just simply plug the values of 12 and 6 for x1 and x2 respectively into the original constraints and make sure that they are in fact giving you a value of 42 and over, 60 and over, 18 and over. And that is the end of the simplex method to find the optimal solution for a minimization problem. Thank you.